Hello, everyone. I'm Gianoglio from University of Genova, and I'm going to introduce you our paper titled The Trade-off Between Accuracy and Computational Cost with Neural Architecture Search, a Novel Strategy for Tactile Sensing Design. Okay, let's consider to have a sensor array that interacting with the environment produce some raw data, and also to have embedded electronics close to this array that has to elaborate this data. So there is on board an ADC, for example, to digitize the data. And also an elaboration system that has to process this data. So on the elaboration system, we can find two modules, that is signal processing and also machine learning model. The signal processing, of course, has to process the data, to filter, for example, the data. And the machine learning model has to extract some valuable information. Then the embedded electronics has a limited power budget, of course, and also a limited storing capacity. And the elaboration system affect these two parameters. Okay, so for example, the machine learning models has some parameters to be saved on the flash memory, for example, and also some parameters that have to be loaded during the inference phase. And also the signal processing affect the computational cost of this device. So our goal here in this paper is optimize this elaboration system, balancing the effectiveness that can be, for example, the accuracy of the model, if we are speaking about classification problem, and also the computational cost. Our strategy is based on evolutionary neural architecture search. And now I present you a quick block diagram. In step one of our strategy, we have to define a pool of possible hyperparameters of our machine learning model, and also a pool of possible techniques that can be used to filter the data. And the step two, we have to pick one of the processing technique and also to generate a model between the possible choices of hyperparameters. Then we have to train this parent model on the data that have been processed by the processing technique and evaluate a loss function to get a score. This loss function is a custom loss function that has been proposed recently and published on IEEE Sensor Journal. And it keeps count of the effectiveness, okay, for example, the accuracy that I mentioned before, and also the computational cost that is weighted by a parameter, theta, that is user-defined. For example, theta equal to 0, it means that we are giving importance only to the accuracy, to the effectiveness. Theta equal to 1, for example, means that the computational cost and the effectiveness have the same importance. And of course, if this parameter is greater, it means that the computational cost is more important than effectiveness of our model. Then step 4, we have to modify, according to the NAS, we have to modify the parent model accordingly to the pool of possible hyperparameters, and we are picking a new technique to process again the data. And step 5, we train again the modified model and evaluated the loss function. If the loss function gives us a better score than the previous one, we will keep the modified model as the best, and also we will keep the processing technique as the best. We will repeat these two steps, so step 4 and step 5, until a stop criterion is met, for example, the number of iteration, or maybe also the number of the accuracy that doesn't get better with respect to previous results for a number of iterations. At the end, what we have is an optimized model and also the signal processing technique, and these two have to be implemented on our device, on our embedded device. We validated this strategy by performing a test on a known dataset in the state-of-the-art, this touch modalities classification problem that include 3 classes of actions performed on a sensing patch, 4x4 sensing patch as an array of piezoelectric sensors, and 280 data have been collected for each class, and each datum consists of a tensor that is 4x4 times 30K samples. Then we decided to compare 3 convolutional neural networks, 1D convolutional neural networks. The first one that we call the standard means that the weights and the activation function are represented with the 32 bits. Then the second one is the binary weights network. That means that the weights are represented with only 1 bit, so -1 or 1. And the third one, the third network, is a full binary network, so it means that the weights and also the activations are represented with 1 bit. And of course, concerning these models, we define a pool of hyperparameters that in our case means changing the number of filters, for example, and the kernel size, for example. And concerning the techniques, we decide to use 4 techniques, which one is no filtering data, so just keep the raw data, plus the moving average to reduce the number of samples, because it is a very huge number, so 30K. Applying the moving average technique, so we are able to reduce this number, in particular, to 25, 50, and 100 samples in this case. For the step 2, so we pick one parent model that we decided to have only for convolutional blocks, okay, and a signal processing between the ones that I showed you before. Then for the first, so for the step 3, the first step of training the model, the parent model, we train this parent with the data that have been processed by the signal processing technique. Then we evaluated the loss function, how, with 2 criterions that have been compared in the results. The first one is counting the number of floating point operation for both signal processing and also the machine learning models. And the second one is the memory occupation that has been measured as the number of elements that must be loaded in the RAM during the inference. And the largest memory occupation is the biggest tensor processed by the system, okay? For step 4 and step 5, we applied 2 mutation each time at each iteration. That was adding or removing a convolutional block, of course, putting a limit to the minimum number of blocks that the model should have, and also to the maximum number of models, because if we put, for example, 100, of course, it doesn't fit on an embedded device. And also the second mutation is a random mutation to one of the existing convolutional layer. So changing, for example, the number of filters or the kernel size. And the stop criteria was where maximum number of iterations, and also an early stop criterion on the number of times no children achieved a better, so children is the modified model, achieve a better score than the parent model. Now I'll show you the results. The first 2 lines correspond to the references in the state of the art. The first one is one of the previous, our previous work, where we achieved 85% of accuracy in the same problem, of course, with a number of flops, 1.31 millions. Instead, the second lines correspond to the best in terms of accuracy in the state of the art, where the authors achieve 85.4% of accuracy, but the number of flops were very high because they used a kernel-based method that consume a lot of energy, okay, so a lot of parameters to be implemented. First results. So in this table, I didn't put the results concerning the full binary network because it didn't achieve very good results in terms of accuracy, and also for the computational cost, it didn't prove any advantage with respect, for example, to the binary weights, where we clearly see that the computational cost is lower, okay, with respect to the standard network. In particular, the line that is highlighted corresponds to the best accuracy that we achieved, that it is 87.6 with the theta equal to 0. So it means that we didn't measure the computational cost during the process of the neural architecture search. And of course, we can see also that the number of flops is higher with respect to our reference in the first line. Instead, the one that is highlighted now corresponds to the standard network with the memory occupation loss with theta equal to 1 and theta equal to 5. So it means that the computational cost is important, especially with theta equal to 5. And we can see that this one is a good compromise because we have, okay, slower accuracy with respect to standard network with the theta equal to 0, but also the number of flops is lower to that one, and also lower to the ones with the ones in the state of the art. So almost the half with respect to the state of the art in terms of flops. And the memory, the memory parameter wasn't measured in the previous works. And here we can see that we have 800 elements that have to be loaded in the RAM memory. Okay, and the biggest tensor has 800 elements to be loaded in the memory. Instead, the last result that I highlight, we have the binary weights network with both losses, and we can see that in this case the accuracy is lower with respect to the standard network, but the computational cost is better. Okay, so for example, if we have other constraint in our device, we can see that the binary weights maybe can be a good option. Okay, instead, if we don't have particular problems to implement the model, okay, so it's, say, more, not expensive, but more powerful board, for example, more powerful device, we can choose the standard network because it has a good compromise between accuracy and computational cost. But binary weights, it's a good option when the computational cost matters more than accuracy and the effectiveness in our case. Conclusion. We propose a tactile elaboration system using evolutionary neural architecture search, but actually this proposal can be used in many other applications, not only in tactile elaboration systems. So you can use this when you have something to elaborate, okay, something to implement on an elaboration device, an embedded device. And this proposal is based on a custom loss function, so evaluating the custom loss function. The standard CNNs achieve the best accuracy and outperform the state of the art, and the binary weights present a better computational cost with a drop in accuracy. In the future, we want to implement our algorithms in this embedded device and sensorizing the harness end in the picture, because we want to use this harness end to, let's say, to interact with the environment, retrieving some properties of the objects during the iteration. Thank you for your